Okay, so this is the stuff that I've learned till now in group theory. So some prerequisites. I already was kind of good at number theory, right? I mean, completed a bit of syllabus for number theory. So I could understand some of the stuff. Actually, you don't even need number theory for this. Like, just go learn the definition of mod, congruences, the Euclid's theorem, right? I mean, what do we call it? Euclid's division lemma, right? That. Uh, and yeah, then you'll be good to go. Oh, and also the algorithm to find GCD, right? The division algorithm. You should probably learn that as well, right? So let's start. Um, so instead of starting with the definition, I want to start with something less abstract, namely some examples of groups, and thus form some motivation to study groups as an abstract structure. All right. So first of all, just consider the group that we call D3, right? So it's made by rotations and reflections of a triangle, and not just any rotations and reflections. The rotation and reflections such that the triangle superimposes on itself after the rotation or reflection. So say you have this ABC triangle. Well, you can rotate in three different ways such that it would superimpose, and then you can also reflect and rotate. But the good thing is that all of these reflections and rotations, well, they can be thought of as just reflections. So just fix one of the points and then swap the other two, right? That's how you get these reflections. And so all of these combined, R0, R1, R2, S0, S1, S2, that is a group. Now we'll study what a group is, but for now I'm just calling it the group D3. You can think of it as the set D3. So for now the word group and set are kind of similar, although we'll learn what a group actually is later. And these rotations can be thought of as matrices, right? So if you're thinking of some linear transformations, then the rotations can be expressed as matrices in that case, and similarly the reflections can be expressed as matrices in that case. And then of course your ABC must be the points given by these coordinates, right? So anyone who has learned like a bit about complex numbers, like you already know about these rotation matrices, right? The reflection matrices are, well, you know what, I'll post a separate video on the proof of these formulae later, right? I shouldn't say these formulae, I should say these formulae. I hope that my pointer is visible though. I mean, I'm assuming it is. Anyway, the set of these 6 transformations has some nice properties. First of all, it has closure over the operation that we call composition. So you basically just matrix multiplication in this case. So function composition, that operation is the one I'm talking about. In the end, these are functions that we're talking about, right? But in this case, these are also matrices, so you can think of just matrix multiplication as that operation. So it has closure over that operation, the set or group D3, whatever you wish, and it has associativity over the same operation, and every element has an inverse, and there's a special element called the identity element, such that the identity element times any other element from D3, that is just the other element. So in this case, the identity element is the identity matrix, which is R0. Just put 0 in this formula and then yeah, it works. So this holds even when we generalize from n equal to 3 to arbitrary number of sides of a regular polygon. So the dihedral group is not just for the triangle, instead it's for any polyhedron. I should say the polygon, not a polyhedron. Fine, so any polygon. And the reason we put a die over there is because this polygon, we don't think of it as just some 2D thing, we think of it as something that has two sides. So you can also reflect the polygon, and that's why die. So two polygons, if that makes sense. In any case, so you can generalize to n sides, and then you would have our elements of our dn being these 1 r square r power n minus. Actually, you know what, that's kind of fast forwarded, right? Yeah, so your elements would just be r0, r1, r2, so on till rn minus 1, and s0, s1 till sn minus 1, where s, k and rk are given by these formulae. Rk equal to the rotation matrix of 2 pi k upon n, and Sk is the reflection matrix of 2 pi k upon n, where R of theta is the rotation matrix, S of theta is the reflection matrix. I mean, yeah, of course the reflection matrix about y equal to x tan theta, right? And the rotation matrix is just bi angle theta, rotates counterclockwise. Okay, so now it's easy to see by some trivial calculation that Ri as j, that's equal to Si plus j. So once again we are doing function composition or matrix multiplication, whatever you like, and then SIRJ, that's Si minus j, and then RIRJ is Ri plus j, and SISJ is Si minus j. Now we can boil down all of this to some simple equations. The equations are that R power n is equal to S square equal to 1, and SR equal to R negative 1s. So R inverse, it's also R n minus 1, because R power n is 1, right? So it's R power n minus 1 as well. And some people write it as R power n minus 1. I prefer it as R inverse because it's, I don't know, you don't need to write n over there, and I just like it like that. Yeah. And so we can define dn even more compactly. Oh, I didn't explain this change of notation, did I? Yeah. So all of this can be boiled down by, well, just changing our notation a bit. Instead of using these subscripts, we'll just set R1, this should be R1 over there. Yep, that's better. So R1 to be R, R0 to be the identity element, which is 1. Just calling it 1. Of course, I should probably call it the identity matrix, but just calling it 1 for now. Okay, and S0 is S. So yeah, S0 is not 1. S0 is actually a reflection, so it can't be the identity element. And R sub k is R power k, right? We can write R sub k as R power k because of this third equation over here in this, right? Yeah. And you also have S sub k equal to R power k times S, and that's basically because of the first equation, right? And because of associativity. Okay. Yeah, and thus your d sub n, the group that we're talking about, that can be just written as this thing, 1 r square up till r power n minus 1, which is, that was basically r0, r1, so on. Now in this case we are writing it using just r, the letter r, no subscripts, right? And the other elements, the reflections, so that s, rs, r square s, and so on. So some things are pretty easy to see. The first is that applying a reflection to itself, the composition of the same reflection, that would just give the identity element, because you reflect once, reflect twice with the same axis, you just get back the same thing, right? And applying any of these rotations n times, that just gives the identity element as well, because all of these can be thought of as roots of unity. If you know about complex numbers, you would know what I'm talking about. But in any case, that's pretty easy to see. Just use the definition of the matrix definition that I've written over there, and just calculate. It's pretty easy to see that. Okay, so finally getting to this definition. So these triangle brackets, it's the generator notation, which means all powers of. So for example, the generator, so when you put like these triangle brackets and then the generator is small s, then that's all powers of s. So s power 0, s power 1, s power 2, so on. Even the other integers, so like s power negative 1 and so on, that also is there. So it's just 1 and s, because s square is 1 and s power negative 1 is s, and so yeah, it's just 1 and s square, which is s power 0 and s power 1 in the simplest terms. Okay, similarly the generator being r, small r, that would give us this set. It's 1 r, r square, so on till r power n minus 1. So this thing over here, you have two generators in there, r and s. That is, you want all powers, actually all compositions of powers of r and s in this case. under the rules that r power n is s square is equal to 1 and that sr equal to r power negative 1s, or r inverse s, if you will. Okay, so that was all about the dihedral group, and to get more familiar with this group, I suggest that you go online and search for some practice problems on this. I mean, really, some like simplification problems. Yeah, that will get you familiar with it. And so if you just think about this this thing, the triangle bracket r thing, well, that's pretty much the roots of unity. So you can do algebra with that, with both operations, addition and multiplication or composition, right? And yeah, these are used, like this thing is used a lot. I mean, of course, it's used as complex numbers, not as matrices, but still. So it's worth to study this thing, I think. Okay, then let's talk about another kind of group. It's called the permutation group. So permutation is any bijection that goes from a domain to the same set, basically. So your subdomain is equal to your domain, and that bijection is called a permutation. So basically, yeah, any bijection where domain and subdomain are the same, it's a permutation, because it just shuffles your domain, right? Shuffles the elements, maps them to something else in the domain itself. So permutations can be described in a more compact notation than the usual map description for a function. So for example, if you have this permutation, so from the set 1 to 3 to the set 1 to 3, right? You can write it in the map description like this. So you have the set 1 to 3 and the set 1 to 3 over here, and you have these arrows describing where the elements go, right? So f of 1 would be 2, f of 2 would be 3, f of 3 would be 1. But you can just redraw this as 1 goes to 2, 2 goes to 3, and 3 goes back to 1. So that's a cyclic notation. Or if you want to write it, then you can write it as this. So square brackets 1 to 3, square brackets closing. People use parentheses, I know, but for like, yeah, for my notes you will only see square brackets because that's what I like, and these are my notes. So yeah, I get the privilege to choose whatever notation I want. But yeah, usually you will see parentheses, and I don't like that notation because it gets confused, like it gets confusing, since we also use parentheses when we want to show that a function is being applied on something else, and so that's why I use square brackets. Okay. Similarly, let's consider this. X is 1 2 3 4 5 till 7, and then f is going from x to x. It's given by this map. So 1 is going to 2, 2 to 3, and 3 back to 1. That you can draw using just a cycle, a cyclic notation. And 4 is going to 5, but 5 is going back to 4. So once again a cycle, 4 to 5, 5 back to 4. And 6 is going to 6, 7 is going to 7. So nothing's happening to 6 or 7, right? It's kind of boring over there. So since nothing is happening to 6 or 7, in our cyclic notation we can drop 6 or 7. Oh, and by the way, for different cycles, all you have to do is just put them next to each other, and person will understand what you're talking about. So this permutation can be written like this, or you can simplify it even further as just 1 2 3 4 5, ignoring the cycles with only one element, because really nothing's happening over there. So although the domain is of 7 elements, you only need 5 elements. You only need to write 5 elements to write down the whole function, and then it's assumed that other elements were not moved in the permutation, right? So even if your domain was like of something bigger than 7 elements, say you had 9 elements and you had 8 going to 8, 9 going to 9, well, you can just write this much, right, and ignore everything else because nothing is happening over there. And in fact, you can also think of this permutation as being 4 5 that cycle, and 1 2 3 that cycle being composed with each other. So the cycle 4 5 would just mean that 4 is going to 5, 5 is going to 4, 5 is going to 4, and nothing else is changing. So 1 goes to 1, 2 goes to 2, 3 goes to 3, everything else stays the same, but 4 and 5 get exchanged. So there's that cycle, and then 1 2 3 is just this cycle without anything else happening, so 4 is still going to 4 and 5 is going to 5, right? But when you compose these, you basically get this thing, right? Yeah, so you can think of these like being applied one after the other, so now they are composed. Yeah, so where both are permutations defined for the same x that f is defined for, of course. So the same capital X, that just means this set 1 2 3 4 5 6 7. Cool. So basically you can write 1 2 3 4 5 of x, that whole permutation applied on x, that's basically the individual cycles applied on x. So I guess at this point you're already confused, but remember these functions are so these permutations are functions in the end, right? So not just mappings, but these are functions. I mean, you have to put things inside for some output. Okay, and that's why I use square brackets and not parentheses, because parentheses would just confuse the hell out of everyone. So just stick to square brackets. So this is a good time to go on the net, solve some basic simplification questions. Once again, familiarize yourself with this notation. So the way you usually simplify stuff is, of course, just by figuring out what is some element going to. So you would just put 1 in there and then check, oh, it's going to 2, right? If it's going to 2 in the whole permutation, and then you would say, okay, so if it's going to 2, what is 2 going to? And then so on until you end with a cycle. Once the cycle is ended, you just go for the next element, the next smallest element which hasn't been used in that cycle, and then just you repeat the whole procedure, right? Yep. Okay, so using that you can, of course, derive this property. So let's say you think about what happens to A when you pass it in this permutation on the left. Well, A first of all does not get changed by the right cycle because nothing specified about A, so we're just assuming it stays the same. But the left cycle changes it to B, so A goes to B, and you have to write that in the right hand side. So A goes to B. This is the first cycle that you're writing. There might be multiple cycles after that, but in this particular case there's only one cycle, so that's nice. Right. What about B? What happens to B? Well, B gets sent to C, but then nothing's happening to C in the next cycle, so in this smaller cycle of 2 elements. So that just means C, so B just goes to C, that's it. Then what happens to C? Well, C goes to D, nothing specified for D in the next one, so you just, yeah, C goes to D, and so on for all the other elements in the right cycle. Okay, so this is like pretty easy to verify, but it's very useful because using this property you can start breaking any permutation or any big cycle that you have into smaller cycles, and thus the permutation into smaller cycles as well. So the smallest number of elements in a cycle, well, that's going to be 2. Of course it can also be 1, but then you don't write the cycle because it's not doing anything to a string, so just 2. And these small cycles have a name. These are called transpositions because, well, they transpose elements, right? So A gets switched with B and B gets switched with A. That's not happening with cycles of bigger number, right? They're not switching, they're like cycling. In this case it's a switch basically. Yeah, and it's pretty easy to see that transpositions are their own inverse, right? A gets switched with B and then B gets again switched with A, so A gets switched with A. I shouldn't say that. A gets mapped to A if you apply a transposition to itself, right? Yeah, right. So this I already told you about, that you can write a big cycle as a bunch of smaller cycles, and using that you can of course prove this property. I'll leave that as an exercise. Do it mentally, of course. Okay, so now any permutations, this I already told you about transpositions. Okay, so now using the first equation we can write any permutation, because it's basically just a bunch of cycles, as a composition of transpositions. This decomposition is not unique, right? So for example, just adding 2 more transpositions of the same kind over here basically, yeah, like let's just say S is a transposition, then S squared is also just identity matrix. Why did I say matrix? Sorry. So S squared is also just the identity element. So just putting that to the right over here, that would not change. Uh, that would not change the whole permutation. But it does change the expression, though. I mean, it looks different. You have more transpositions involved. So it's not unique. This expression on the right hand side, it's not unique. You can have multiple such expressions. So what is invariant about this kind of expression? Well, the parity of the number of transpositions used, that is invariant. As in, either you will have an even number of transpositions for this permutation all the time for every kind of expression that you will write for it, or it will be odd all the time. Alright, cool. And this will prove later. So where was I? Right. Yeah, okay, so these are either always even or odd based on the permutation. And so this gives rise to classification of permutations as odd or even. And that also leads to some more definitions. Okay, so since we are composing functions, there's associativity, right? But there's no commutativity, right? You don't say f times so f composed with g is the same thing as g composed with f. There is commutativity sometimes, and that is when your permutations are composed of entirely different cycles. So you don't have any transposition in common. That's basically the thing. So there is a special permutation called the identity as well. I mean, you already know that. So it's denoted by just this. It's a weird notation. So usually you don't write these cycles with only one element, right? But over here you have to write something. So just write the cycle with one. Yeah, one going back to itself. So just the identity function. Yeah, or the identity permutation, I should say. So right, just to reiterate, your operation, the function composition, it has these properties: associativity, not commutativity yet, right? It will be in a special case, of course. There is a special permutation called an identity for this operation of composition of functions, and every permutation has its inverse. So every function has its inverse. That's thing, right? Yeah, right. Okay, so now consider the set of permutations from x, which is 1, 2, 3, n minus 1, n, to x itself, again, to as permutations. So now you consider the set of all these permutations, right? So Sn is this set. It's all functions going from x to x such that there exists an f inverse, which basically means that f is bijective, because these two conditions are the same. Having an inverse and being bijective are the same thing. Okay, and of course x is this 1, 2, 3, 4 till n. So Sn is called the permutation group in n, and it has nice properties. It has closure over the binary operation of composition. So you take any two elements in Sn, compose them, you just get another element in Sn, right? And that means that the composition of any two elements in any order, I mean, okay, that I just explained. Why am I reading this? Yeah, right. Oh yeah, okay. So this is about the order of cycle. I guess it's misplaced. So it's easy to see that applying an n cycle with n elements involved n times to any element gives back the same element. What that means is that, so it's easy to see in this picture, I guess. What that means is that composing an n cycle with itself n times, well, that gives us the identity, because it's happening for all elements, of course the elements involved in the cycle. For other elements that are not involved, well, it's already behaving like an identity in any case. And I should move this picture down, so I guess over here. Okay, next. So when can two cycles commute? I talked a bit about commutativity, and I said that two permutations can commute if they don't have any element in common. So first of all, when can two cycles commute? Two cycles, if they have no element in their cyclic element common in their cyclic notation, then you can commute them, right? Because it's like they're working on separate domains. I mean, it's as if they're working on separate domains because everything else is just the identity. So applying 1 2 first and 3 4 5, that's no different than applying 3 4 5 and 1 2, and you can verify that, simplify it as you want, right? Simplifying this right hand side to the left hand side, that's kind of an easy job. You just start with what happens to the element 1, and then the next element, and then the next element that 1 is mapped to, then one that element is mapped to, and so on. So in this case, 1 is mapped to 2, 2 is mapped back to 1, so you close the cycle, right, when simplifying the right hand side. And then you go for the next smallest element remaining. So 3 is remaining. So just check what's happening to 3. So 3 goes to 4. So you write that over there. That 4 goes to 5 when you pass it to this permutation. You write that there, and 5 goes to 3. So you close this cycle. Okay, order of a permutation. So more generally, the order of permutation. So you already saw the order of a cycle. What about the order of the permutation? The order of permutation is defined as the minimum number of times you must compose the permutation with itself to get the identity, and it's not the number of elements involved, right? Okay, so we know that the cardinality of Sn, it's the same as the number of permutations of the numbers 1 2 till n, right? Yeah, I mean, that's pretty obvious because Sn contains all kinds of permutations from x to x. So the cardinality of Sn is just the number of permutations, of course. So basically, the cardinality of Sn is n factorial because from combinatorics, you know that number of permutations on n distinct objects, that's just n factorial. So now consider the sequence p square, p cube till p power k for some permutation p, which is a part of Sn. For k bigger than n factorial, what will happen is that by pigeonhole principle, you will have two elements in this sequence which will be the same, right? It has to happen because pigeonhole principle. So say these elements are p power a and p power b, then you can just apply p power a inverse or p inverse power a, because p inverse is in your Sn, and then p inverse power a is also there by closure and all that stuff, right? So yeah, just applying p, or okay, p inverse power b also works fine. So what you get is that p power a minus b, assuming a without loss of generality that a is bigger than b, just assume that. Even if you don't, like, it's still true, it just it's not very convincing. So okay, p power a minus b, that's equal to the identity element. Just applying that on applying p power negative b on right hand side and left hand side, you just get this thing. Right, but that means that p to some power is the identity element, which means that every permutation does have an order, right? And of course a, b are different. Yeah, okay, and also it's easy to see that if the order of p is m, then p power k equal to 1, that's the same thing as m divides k, right? Because, well, it's the minimum number of times you must compose itself, right? And then you can think of k being something like mq plus r using the Euclid's division algorithm, division lemma, right? And then you just have to prove that r is 0, which is easy, right? And then yeah, you just get this thing. Okay, so now here's a little question for you to be interested till now. So you want to find the order of this permutation 1 2 3 4 5, and they haven't given, or I haven't given because I was the one writing notes on what kind of set you are doing this, but you don't need to know that anyway, right? Because it doesn't matter on what x you were doing this, since everything else would be the identity element, you might as well ignore everything else. So just think of this being applied on 1 2 3 4 5, right? That's it. So the two cycles have the order 2 and 3 because you already know the order of a cycle, right? And since the cycles have no elements in common, we can commute them and that means that p power 6 is 1. But by the last discussion that we did, you know that the order of p must be a divisor of 6, so it can only 1, 2, 3 or 6. And then check each of these and you will see, well, okay, none of them work, only 6 works. So in fact it is 6. So that's the way you find order of a permutation. Okay, odd and even permutations. And okay, in general, if you have multiple cycles, you want to go for the LCM of the order of each of the individual cycles, because p to that LCM, that will be 1, right? And then of course you can do some of this as well, you know, that LCM is divisible by the order, and in fact that LCM is the order, I think. Yeah, I mean, at least in this case it was. Okay, odd and even permutations. So you already know the definitions. Now we'll prove that the notion of odd and even makes sense. That is, we'll prove that the parity actually stays the same all the time. So let's suppose that T1, T2 till Tr are transpositions, of course belonging to Sn, right, the permutation group, and that T1, T2, T3, so these composed together till Tr, all of them composed, that is equal to the identity element. Well, then R is even. That's our lemma, and we are going to prove this by induction. So base case, R equal to 1, it's impossible, because well, transposition cannot be the identity element, right? It has to have 2 elements, and identity element has no cycle with 2 elements, of course. And R equal to 2 is possible by setting T2 equal to T inverse, so that T1, T2 is identity element, right? We already found one T2 such that this happens. And I didn't say anything about the uniqueness of these transpositions. Okay, these could be, you know, the same transposition for all we know. All you have to prove is that R is even, right? So our hypothesis is that the lemma is true for, it's called the hypothesis, right? I'm a bit rusty on the terminology. Anyway, so we are assuming that the lemma is true for small r less than capital R minus 2, where capital R is some number. So let's go to the induction step now. Now consider T1, T2 till T capital R, that's the identity element, and assume that T capital R is this thing AB. So now Tr minus 1 can be of four types. Either it could contain A, or it could contain B, or it could contain none, or it could contain both. Well, if it contains both, if Tr minus 1 contains both, well then Tr and Tr minus 1 are the same, and they are also each other inverse, because transpositions are inverse of each other, inverse of themselves. So that just means, well, you've made this this product of T1, T2 till T capital R, this product, to now be T1, T2 till T R minus 2, and now it has R minus 2 transpositions, and that's the identity element as well, and we already proved it till R minus 2, I think, right? Yeah, so it proved it till R minus 2, was that the thing? Oh, it should be less than or equal to over here, sorry. In fact, you know what, let's just say it's less than or equal to R, that's better. Oh wait, that should not have been the thing. So just R, yeah, that's better. So we have not done this for capital R, but everything less than capital R. Cool. So even for R minus 1, by the way. Right, cool. Yeah. What was I doing again? Wait, what was I doing again? Oh yeah, I was going through this list. So your Tr minus 1 could contain both, and then you would immediately get the fact that, oh yeah, this is like working. From the induction step, you went to the fact that T1, T2 till Tr, that's equal to 1, that implies R is even, because R minus 2 is even by the induction step, by the hypothesis, and so R is also even. So in the fourth case, it's pretty obvious what you have to do. In the first three cases, it's slightly not very obvious. So what you have to do is you have to do some observations And the one observation you can certainly do is multiply tr minus 1 and tr, and what you'll see is that you can always write this as something containing a on the left, and on the right you will have transpositions which do not contain a. So you move the last occurrence of a from the rightmost transposition to the second rightmost transposition, and you can keep doing this, right? You can keep moving the last occurrence of a until one of two things happens. Well, first is that it meets its inverse, and then once again you just get to the r-2 length permutation equal to identity element, and you can use the hypothesis and say, well, r-2 has to be even, and then r has to be even. Or it could be that you move the transposition containing a, you move the last occurrence of a all the way to the left, right? So now t1 or t1 dash I should say, because now it's not the same transposition, it's something else, we have changed it. So now t1 dash contains a, and no other transposition in your expression contains a. But what that means is that you can write the identity element as t1 dash, t2 dash, t3 dash, so on till tr dash, but t2 dash, t3 dash till tr dash, that does not contain a. So a, when you pass that in as an argument to this function, the function t2 dash, t3 dash till tr dash, well, you just get back a. Yeah, but then when you pass it through t1 dash, since t1 dash is not the identity element, it sends it to something else, right? So what that means is that a was just sent to something else by a permutation which we thought was going to be an identity, which is bullshit. What that means is that the second case cannot happen. So the first case is the only possibility, and in the first case we already proved that r is even. So there you go, r has to be even. So once again, the lemma was that if a bunch of transpositions put together is equal to the identity element, then the number of transpositions, that has to be even. Alright, now let's go to the fact that the parity of transpositions stays same for a certain permutation. So if you have t1 t2 till tm equal to tm plus 1 tm plus 2 till tm plus n, so on the left hand side you have m transpositions, and on the right hand side n transpositions, all composed. If this happens, then m has to be equal to n in the parity, right? Or I should say m and n are both even or both odd. Yeah, both odd. This is pretty easy really. Just apply the inverse of the left hand side on both sides, and then on the right hand side you'll just get something like m plus n transpositions, because taking the inverse of just show you the whole thing actually. Yeah, this is the whole thing. So just apply sigma 1 inverse on both sides, and you just get this thing, right? So you have n plus m transpositions, and now this product with n plus m transpositions, that's equal to 1. So what does that mean? That means that n plus m has to be even, which means both m and n have to be odd or even, and so m and n have the same parity, which is what we wanted to prove. You can also write it as m congruent to n modulo 2. Okay, and thus any decomposition of a permutation into transpositions, that will always have the same number of transpositions, that will always have the number of transpositions in the same parity, as the decompositions are equal, right? So what we are saying is that in this equation, the left hand side and right hand side, well, they are the decompositions of the same permutation, although we don't know the permutation. But then for any permutation you can do that, right? You can decompose it into a bunch of transpositions. So if you decompose it into different expressions, or I should say different looking expressions, well, the number of transpositions in those expressions, they have to be of the same parity. That's the theorem. I mean, that's the corollary, I think. Well, yeah. So that makes the notion of odd and even have some sense, because yeah. Okay, so now we are going to a definition. We define a sub n to be the set of all permutations in the permutation group Sn, such that the permutation is even. So an is called the alternating group because you skip one permutation and you take the other one. I mean, pretty obvious. So an is made up of all the even permutations and it's called the alternating group in n, and thus the other part, which is Sn minus an, that's made up of all the odd permutations, right? Now consider the function that goes from an to Sn minus an such that the function is basically just applying the transposition 1 2 on the permutation that you pass in the function. It's easy to see that f is a bijection, right, with the inverse being itself. So first of all, it's a convolution, and then it's injective, pretty easy to see that. It's also surjective because you can always find a pre-image, just apply 1 2 and you got it. So what that means is that the domain and the subdomain must have the same cardinality, and what that means is that the cardinality of an is the same thing as the cardinality of Sn minus an, but you know that Sn is just an union with Sn minus an, the disjoint union, of course, because Sn minus an, how could that have anything in common with an? What that means is that the cardinality of Sn is the cardinality of an plus the cardinality of Sn minus an, but these are both equal, so they are equal to the cardinality of Sn upon 2, which is just n factorial upon 2. And so this was one of the kind of useless definitions because we didn't use it later on, but yeah, this is also there in the playlist that I watched. So I watched the Michael Penn's playlist on abstract algebra, and let's be honest, that was, the order was weird, the order of the videos, that was weird in there, but I somehow managed to learn all of this. Okay, right, so now we're finally getting into the actual real group theory, which is done with general groups and not with just the examples that we have. I think I missed a few examples. I missed the unit, the group of units modulo n, which actually I'll cover later, right? That is there. Oh, this is the first example that I do. Fine, there's that example, and there's also the example of quaternions that I didn't do before the definition, but then again you can always do it later on. So first of all, let's talk about what really is a group. A group, denoted as parentheses G bracket and an operation close parentheses. Well, a group is a set with an operation such that first G is closed over that operation. The operation is associative. There is an identity element in G for that operation, of course, and every element in G has an inverse according to that operation in G. So for all A in G, there will exist an A inverse, right? So for example, the real numbers with the operation multiplication, that is not a group because 0 has no inverse. There is no number in the real numbers okay, that you can multiply with 0 to get the identity, which is 1. And similarly, Sn minus an, that was not a group, but an was, an because it was made of the even permutations. Well, it has closure, an even permutation times another even permutation, that's still an even permutation. It has associativity, of course. I mean, function composition always has associativity. There is an identity element because 1 of course can be written as, how do I say this? Well, 1 has no transpositions or 0 transpositions, so it's also even. So it's also in an, and then every element in our an has an inverse in an, right? Because you can just make them as a bunch of transpositions and then apply the inverse, and you just get, like, you just shift the order, and then the transpositions being inverted are just the transpositions themselves. So it's pretty easy to find the inverse. You can just prove that every element has an inverse by constructing the inverse, and of course that's also an even transposition because you just changed the order. That was all you did to get the inverse. So that just means that an was a group, right? And so was Sn, and so was D3 and Dn. So we have been dealing with examples of groups till now, right? So but Sn minus an was not, because odd times odd is even, not odd. So no closure, first of all. there's no identity because the identity has to be an even permutation, right? So that already makes this not a group, right? Yeah. So now let's go to a good example, the group of units modulo n. So the equivalence classes modulo n, well, they are not a group with multiplication because 0 has no inverse once again. That already proves that they are not a group. But we can delete some elements to make it. So for example, this group, so the set 0, 1, 2, 4, 2, 3, 4 till 7 with the operation of modular multiplication. And this is done modulo 8, of course. So this is not a group yet, but the set 1, 3, 5, 7, which are all the numbers co-prime to 8 with the operation of multiplication, well, that modular multiplication, of course, well, that is a group because you see any two co-prime numbers, so any two numbers co-prime with some certain number multiplied together are still co-prime with that some certain number. I mean, they do not have any prime factors in common with that number, right? So that's still there. So there's a closure. There's what do we call it? There's an identity element because 1 is of course co-prime to every number, so that's always there. There is also a notion of an identity. There's also inverses for every single number, and that's because, what was I gonna say? Oh yeah, that's because once again, using the pigeonhole principle, you can prove that the elements of this group, well, they become equal to 1 when you exponentiate them to some power, right? So when you keep multiplying them with each other, you eventually get 1, right, by the pigeonhole principle. So what that means is, like, if let's say 3 power n is equal to 1, then you can just write it as 3 times 3 power n minus 1 equal to 1. So then 3 power n minus 1, which is, by the way, in your set, that is the inverse for 3. And so you just found it. By construction, you can always figure out, I shouldn't say construction, by the pigeonhole principle, you can always figure out, you can always prove that there is an inverse. Alright, cool. And then also there's the other way of proving this. Right. But we'll look for that later. Okay. And actually, no, you know what? Let's look for that right now. So for all x belonging to the group of units written as u in n, of course, Euclid's division algorithm guarantees that there exist a and b integers such that ax plus bn is equal to the GCD of x and n, which in this case is just 1 because co-prime. So that means that ax is congruent to 1 modulo n, just taking mod n on both left hand and right hand side, right? The bn thing becomes 0, and thus a is the inverse of x, right? Because a times x is 1 modulo n. Now from the same congruence, we can see that ax is co-prime to n. So that is, yeah, that is, I mean, of course, because what we just did was we said that ax is, like, ax plus bn is, how do I even say this? Oh, okay, I can say it like this. I can say it like 1 times ax, so ax as a single number, plus b times n, that is equal to the GCD of ax and n, right, which is 1. This was weird. Okay, that's not the way I should say it. You know what, you can prove it by yourself. Come on, you can prove it by yourself. Yep. Yeah, you can actually prove it by yourself. How do I even say this? Okay, so if they had a GCD-G, if ax and n had a GCD-G, then this equation that ax plus bn equal to 1, that would be not good because the left hand side is a multiple of g, while the right hand side is just 1. And of course, g has to be not equal to 1 for them to have other GCD and 1. And that cannot happen, which means that they are co-prime. Okay, so this congruence, that just means, and also this equation, so both of these basically just tell us that, well, ax is co-prime to n, right? But we already know that x is co-prime to n, so a is also co-prime to n, right? None of them should have any factors of n, otherwise the co-primality would be lost. Yeah. So written differently, I mean, okay, you know what, you didn't even need to show that X is co-prime. A is co-prime, both are co-prime because X is co-prime, right? So now written differently, what we just said is that for all X in our group U, A, which is the X inverse, we just proved that, right? AX is congruent to 1. That is co-prime to N, and that's all, and that means it's also a part of that group U, right? And thus the fourth condition is also satisfied, and UN is a group. Alright. So that was a nice example. And this group UN will occur, I guess, later on when I'll study for what do we call it, the Euler-Toshin function, most probably, because that will be there. I think there's a group theory proof to that as well. Yeah, probably missed that video because that was in the reverse order. Fine. In any case, just move on. General properties of groups. First, there's a unique identity for every group, right? Just read the proofs yourself. I'm not gonna go into that. Then there are unique inverses. Then there's also a notion of a subgroup, which is basically a subset of the set used in your group over the same operation, that being a group, right? So a group that is a subset of some other group, basically. There's also a subgroup test that, you know, uses all the four properties that you need for something being a group, right? And you just boil it down to a single equivalence, right? And that's your test for something being a subgroup. It's not a group, a subgroup, because if it's coming from a group, associativity is already there, right? And also something else was it? Oh, right, closure? No, closure will not be there, not necessarily. Something else was there. Oh, right, the identity element. The identity element is already there, of course. And since in the bigger group your identity element was unique, we just proved that already. Your new what do you call it? Yeah, your subgroup, that should also have the same identity element, because if not, something's messed up. You have two different identity elements. That doesn't make sense. Okay, cool. So that's a subgroup test. Just read the proof. I'm not going to go through it. Then you have the centralizer of a group, which is completely useless because I did not use it for anything else. And you have a center of a group, which is based on the centralizer, but just not for a subgroup, but the whole group. Centralizer is basically like all elements of your main group such that they commute with every element in the subgroup. Yep, just a set of all such elements. That's a centralizer. And the center of a group is all elements of your main group that commute with every element of, instead of a subgroup, the whole group, right? So yeah, and then you have something called a conjugate subgroup, which you can also prove is a group. Wow, that was weird. So it's given as G inverse HG, and it's of no consequence to us whatsoever till now because I didn't use it later on. But you can read its definition, its proof here. Come on, just spend 2 minutes pausing the video. Okay, and then every subgroup of a cyclic. Oh, so this is kind of important. Every subgroup of a cyclic group, it's also cyclic. So read the proof for that, but I'll just leave you with the fact that yeah, it does happen. Every subgroup of a cyclic group is also cyclic. Nice. Also, the order of an element in a finite group. Oh yeah, it's just a definition of that, right? Yep. Right. So it's defined as the minimum number of times that you have to multiply the element with itself to get 1. Just like we did with the permutation case, right? Permutation group case. Okay. Then you have the order of a cyclic group. So the order of a whole group is a weird concept to me, but the order of a cyclic group is basically the same as the order of its constructor, and that's also the same as its cardinality, because when you use the constructor, you just like keep multiplying, eventually you get 1, right? So that's, you know, the number of times you had to multiply to get 1. That's also the number of elements that you got. So of course. Okay, now let's go for a lemma, which is that, say if G is a cyclic group, constructed by small g, and that the cardinality of g is the same thing as order of small g is n. You already know that from the definition of the order. Then g power k is 1. That's the same thing as n divides k. So once again, not going to go into the proof at all because it's pretty easy. You can do it. And if you don't want to do it, just read it over here, right? Just pause and read it. Okay, now let's go to a theorem. This keeps on going. There are a bunch of lemmas and theorems. Okay, suppose that once again G is a cyclic group. Then for all natural numbers k, small g power k, the order of that's just n upon GCD of n and k. We can also write this as LCM of n and k upon k. I like it better that way, but whatever. Yeah. So once again, this is like pretty obvious from the definition of the order of g, the order of g power k. So the order of g power k is the minimum natural number such that g power k power m is 1. So g power km is 1. But then g power km is 1, that just means that n divides km, because g is a constructor for our group, right? So basically you're looking for the minimum natural number such that n divides mk. Now mk is a multiple of k pretty obviously, and it's also multiple of n now. So now the minimum such number would be L, and from L you can easily get m as L upon k, right? And so that's what I did, and you basically just get 1 upon k times LCM of n and k, because that's what mk will be. Yeah, and you can write that as n upon GCD of n and k, using the fact that LCM times GCD is just a product. Cool. Now let's go to a corollary. For a cyclic group with order n, the group can be constructed by g power m as well, if and only if the GCD of m and n is 1. Pretty obvious, right? Yeah, because otherwise the order of g power m would be something else, right? It won't be n, it will be n upon something. So then of course the order of this thing g power m would also be n upon something, and that would mean that the order of g is not n, which is stupid because we already said it is n. Okay, next. So next is a very important definition, right? Usually I hate definitions, but this one is pretty important. So it's called a coset of a subgroup. Should be a subgroup over there, not a group. Okay, so the coset of a subgroup is defined like this. Say that H is a subgroup of G, then the left coset of H with the representative element small g is small g times H, or small g applied on H, or I don't know, whatever you call it, small g H, just put them next to each other, which is the set of all small g small h, it's weird, such that small h is an element of capital H, right? And then similarly you define the right coset, whatever. So why is this important? Because this will be useful in proving something that we call the Lagrange's theorem, which is pretty nice. So first lemma that we want to prove with this definition is that different cosets are disjoint. This is already a very big thing, right? Actually it's a very big thing. Okay, so let's do it using proof by contradiction. So suppose that these were not disjoint, that there was an x which belong to both g1h and g2h. Then what we can do is we can express h as g1h and g2h, g1h1 and g2h2, but h1 h2 are just elements of capital H. But what that means is that g1 is equal to g2 h2 h1 inverse, right? And then you just right multiply with small h, which is an arbitrary element from capital H. So that means g1 small h is equal to g2 h2 h1 inverse small h. But then this whole thing in the parentheses, h2 h1 inverse small h, well, that's also an element of capital H by the closure property and the fact that the inverse also lies in the capital H and all that stuff. But what that means is that you just did g2 times something that belonged from H, which now belongs from g2 H, right? Yeah, that coset. But what that means is that for any arbitrary small h, you have g1 small h belonging to g2h, right? The coset g2h. But remember that g1 capital H, that coset, that was built by this definition. It's all small g1 small h such that small h belong to capital H. But then every of these elements, well, they belong to g2h. What does that mean? That just means that g1h is a subset of g2h. But then by similar logic, you can, and by symmetry, you can just say that g2h is also a subset of g1h in that way. We could have just switched these subscripts and that would have made sense. But what that means is that you can say, okay, then the only way is that both of them must be equal. So g1h is equal to g2h, but that is wrong because we just said that these two are distinct cosets. So what that means is that our assumption is wrong, that there cannot be an x which is belonging to both g1h and g2h. What that means is that they are disjoint. Cool. Next lemma is that distinct cosets of capital H in G, they partition G. So honestly, I'm not going to do this, but there is some like subtlety that I do have to tell about. So actually, I should probably do this. So the proof is that for all elements of G, small g, say, small g belongs to small g capital H because, well, H contains the identity element. So yeah, it's there. Small g times H, it also contains small g as the very first element that you will write down. And thus small g H is a coset which contains small g. For any arbitrary g, you could always find a coset like that. And by the previous lemma, we also know that small g can only be in one coset. It can't be in multiple cosets. Then those two cosets will have some intersection, which is stupid. Of course, our different cosets cannot have an intersection, right? So now we know that for any element in G, you can always find exactly one coset of H in which it is, right? And thus capital G is partitioned by the cosets of H, right? So some people might think, okay, so doesn't that mean that you will have the number of elements in capital G, those many number of cosets, because every element belongs to a different coset, right? Yeah, I mean, every time you will have to introduce a new coset. Isn't that right? The thing is, no, you can reuse the cosets, right? So G belonging to GH, that does not mean that, okay, how do I say this? That does not mean that GH was just invented, right? I mean, you just inserted GH. No, it might be something that you have already used while putting other elements in the coset. It's just that G1H and G2H could be the same coset even if G1 and G2 are distinct, right? So G1 and G2 not being equal, well, that does not imply that G1H and G2H are also distinct. Otherwise, of course, you would have like cardinality of G, those many number of cosets every time. That's not the case. For example, for the group D3, you have only two cosets, considering the subgroup being the cyclic subgroup generated, the cyclic group generated by small r, right? There are only two cosets, which are namely the cyclic group R generated by R and S times that. Alright, so only two cosets, but the cardinality is 6. So of course you don't have 6 cosets, right? Okay, so let's go for the next lemma, which is that the cardinality of H, that's the same thing as the cardinality of every coset of H. So the informal proof for that is, well, the function that is multiplying by G, that's a bijection, so pretty obvious. So for every element in H, you get a GH, right? Yeah, and you get a distinct GH because it's injective. You can apply G inverse on the images, and right. So it's a bijection basically. Yeah. Of course, the dominance of dominant of the same size and all that stuff. Whatever. This is pretty easy to prove. Let's go to the next thing. the next thing is a big thing because it's the Lagrange's theorem. Lagrange's theorem states that if H is a subgroup of G, and then we define this thing to be the number of distinct cosets of H in G, then the cardinality of G is the cardinality of H times the number of distinct cosets of H in G. So it's pretty easy to prove because of all these three lemmas that we have proved so far. So of course you can partition G in all these cosets, right? So you can write the cardinality of G is just the sum of the cardinalities of these cosets, but then every single coset has the same cardinality, which is also the cardinality of H. So now you just want to do cardinality of H times the number of cosets that you have, which we just define to be this weird notation. Yeah, so just write it like that. Cool. So this was very easily proved, but actually you shouldn't just dismiss all of this groundwork that we did. These three lemmas are just as much important as the actual Lagrange's theorem, I think. And most importantly, the fact that the cosets are disjoint, that's like important, I think so. Okay, so now let's go to some good corollaries of this theorem. So first corollary is that for a group G with order n, not the order, the cardinality n, right, sorry. So for a group G with cardinality n, we have that for all small g belonging to capital G, so for all elements of capital G, the order of these elements, well, that divides n. Yeah, right. And this is for every group, not just cyclic groups, not just some special case, every single group. This does happen. The proof for that is just construct the cyclic group with a generator G, the small g element that we're talking about, and that will be a subgroup of capital G, of course. So now applying Lagrange's theorem, we can see that capital H must divide capital G, right, because of this equation that we have in the Lagrange's theorem. But that just means that capital H, which is so the cardinality of capital H, which is just the cardinality of this thing of the cyclic construct, the cyclic group constructed by small g, which is also, by the way, just the order of G. That is the thing dividing the cardinality of G, right? And so that's it. We just proved that the order of G is a divisor of n. Easy as that. Let's go to the next corollary, which is for a group capital G, if the cardinality is a prime number, then G has to be a cyclic group. It has to be a cyclic group. And the only subgroups of this group are capital G and the group containing the identity element. That's it. The set containing the identity element. That's it. Those are the only two subgroups. And this is like pretty easy to show because any subgroup, its cardinality must divide a prime number, so it can only be 1 or the prime number, because those are the only two divisors of a prime number, right? And so from there it follows easily. And then similarly for any element of G except the identity element, you can say that its order divides the prime number P, so its order must be the prime number P because its order cannot be 1. That would be the same as saying it's the identity element, right? Because G power 1 is the identity element. That would be the thing, right? So the only way is that its order is the prime number P, right? But then P is the cardinality of G. So what you just did is that its order is the cardinality of G, right? So the cardinality of the cyclic group constructed by small g, which is a subset of G, by the way, that has the same cardinality as G. So what that means is that capital G is just equal to the cyclic group constructed by small g. And so there you go, easily proved. And that's it. I'll stop for now. See you guys in the next video.